Hello, welcome to my live session. I think we're up and running now. It's been a while since I've done a live session, but my students have asked me to do one for their rates of reaction quiz that they have tomorrow. So we're going to go over 5 questions from a previous quiz that I've done for our rates of reaction in grade 12 chemistry. If you have any questions, let me know in the chat. If you're having trouble with the audio or there's any other issues, let me know so that I can try and fix that. Okay, otherwise I think we are good. All right. First question. Explain the effect of temperature on the rate of a chemical reaction. So you might remember, well, my students might remember in class, we did a lab. This lab is also on my channel if you want to watch it, but we look at the different factors that affect rates of reaction. One of them is temperature. So if we want to look at how the temperature affects the rate of reaction, I have to think of collision theory. So increasing temperature means you're giving particles a lot more energy. Not only do they have more energy, that extra energy, or to put it, that extra energy gives you a higher chance for a successful collision and therefore a reaction. Okay, you can also have more collisions actually occurring if particles are moving around faster. It's like watching a video in 2 times speed, right? You'll see more collisions occurring. Okay, so that is something you'll just have to write and explain. But I just talked about it, so I'm not going to spend time writing it all out. Let's go to question number 2. We have to construct a potential energy curve for this following hypothetical reaction here. So A2 plus B2 gives you 2AB. First thing you need to notice is that the enthalpy change is negative. That means this is an exothermic reaction. Okay, and then we have a certain amount of activation energy. So if we were to draw, okay, since it's exothermic, we're going to start up here with a certain amount of energy for A2 plus B2. And then we're going to end somewhere down here. Since it's exothermic, that energy is being lost. Okay, and that will be our 2AB. Now we're not going to just simply connect it like this because we require a certain amount of activation energy. So I'm going to try to draw a curve here on my computer. But something like that. Okay, so this distance here, or this portion, is our activation energy. So we're going to write that as 15 kilojoules. And from here down to here, that is our change in enthalpy, which is looking at the enthalpy we had during the beginning with our reactants, comparing with the enthalpy we had during our product. So down here is delta H. Okay, specifically we have 65 kilojoules, or minus 65 kilojoules. It's a drop in 65 kilojoules. So minus 65 kilojoules. Okay, and that's all you need to do for that. Part B says, how would the curve change if a catalyst were added? So if a catalyst is added, it's going to reduce the activation energy required. So you just need to make that first bump a little smaller, like that. So you have a much lower, same enthalpy change, but a much lower activation energy if a catalyst were required. All right, does anyone have any questions? Are we good? Can everyone hear me okay? I'm going to assume yes. Okay, so moving on then. We'll go on to question number 3. Consider the following hypothetical elementary process. Now that's very important because it says it's an elementary process. It means we can write the rate law directly from the reaction. There is no mechanism required. We'll talk about mechanisms in question number 4. So part A, so 3A, says write a rate law expression for the above reaction. So we're going to use our reactants. So our rate law is going to be R, the rate equals K, where K is our rate constant. And we're going to multiply by the concentration of X and take that to the power of what our coefficient here is. So there's a coefficient of 1 technically there. We just don't write it. So that's the power of 1 if you want to write it. Then multiply by we use square brackets to denote concentration of Y, and then to the power of, so our coefficient here is 2. So there's our rate law, which we can get directly from the equation if it's an elementary process. All right, next one, 3b. This is one where students make lots of mistakes on. How would the initial rate of reaction be affected if the concentrations of both X and Y were doubled? All right, so let's look at our rate. If we have a new rate, let's just call this R prime. So a new rate is going to equal to K. And we've got twice the concentration of X to the power of 1 and twice the concentration of Y squared. So if I pull out those coefficients there, so we have a 2 times by, here we have a 2 squared. Hello. And then we'll just leave the rest. So K, X, and Y. So 2 squared is 4 times another 2 is 8. So we get 8 times this. I forgot the squared there. 8 times that. And that is our original rate. So our new rate becomes 8 times the original rate. So how would the initial rate of reaction be affected if both concentrations of X and Y are doubled? It increases by a factor of 8. So increases by factor of 8, or just 8 times if you prefer. Okay, so that's how we do question 3. Does anyone have any questions so far? All right, everyone can hear me okay? I hope so. Okay, let's move on then to question 4. And if anyone has missed me going over questions 1, 2, and 3, when I'm done the live, you can go back and watch it because it'll be immediately posted on YouTube. So question 4, considering the following reaction and its experimentally determined rate law. So here's the reaction, here's the rate law. Does this reaction represent an elementary process? Well, notice here we have a coefficient of 2 in front of the nitrogen dioxide, whereas in our rate law, the exponent is a 1. Those do not match, so no, this does not represent an elementary process. What is the order of the reaction? Well, we're going to look at the rate law, and we're going to look at those exponents for each concentration. So we have a 1 above nitrogen dioxide and a 1 above fluorine. So we just add those exponents. So the order is just going to be 1 plus 1, which is 2. So our order is going to be 2. All right, next part, C. Again, the one students have trouble with. Propose a simple 2-step mechanism for this reaction. So this is how we're going to do it. The first step, step 1 we'll call it. It's easiest if you make the first step follow with the rate law. So the rate law has a nitrogen dioxide to the power of 1. So let's just have NO2 with the coefficient of just 1 in front. And then fluorine with, again, just the coefficient of 1. And then what we're going to do is we're going to try and create as many of our products as we can. So notice we can create an NO2F, but we can only create one of them. Okay, we have another F left over, so I'm just going to go plus F. And then whatever we have left over, which is this F here, we're going to pull that down into our second step. So our second step we'll start with whatever we had left over, and then we're going to add whatever we didn't use from this original equation in step 1. So in step 1, I used 1 mole of nitrogen dioxide and 1 mole of fluorine, but the equation says there's 2 moles of nitrogen dioxide. So I'm going to use that second one now. And then combine them together to get the remaining products that we're looking for. So we already created 1 mole. Let's create the second one. So NO2F. And then it says, very important, remember to identify the rate determining step. That is the slow step. So the first step is the one that follows the rate. It's our slow step. And the second step is our fast step. All right, everyone okay with that? Any questions? Nope. All right. Moving on then. Last question. Again, lots of students have a lot of trouble with this one. Let me just scroll the page down a little bit there. Okay, so for this one, we have to use the available data. So down here, so an experiment was done. Use the available data to determine the rate equation for this reaction. Now we can't do what we did in question 3, because question 3, it says it's an elementary process, and so we just wrote the rate directly from the reaction. That's not necessarily true here. We have to look at the experimental data. So let's start by looking at how we got nitric oxide here. How does its concentration changing affect the rate? So to figure that out, we need to look at what 2 trials keep hydrogen constant. So hydrogen is constant in trials 1 and 2. When hydrogen is constant, nitric oxide goes from 0.01 to 0.02, so it doubles. So what happens to the rate when nitric oxide doubles? The rate goes from 4 to 16. That means it quadruples. If one doubles and the other quadruples, this is essentially a quadratic relation, right? It's like saying y is proportional to x squared, right? If x doubles, y quadruples because y is related to x squared. So let me get rid of that before my students get mad that I'm doing y's and x's in chemistry. So what this means is that the rate is going to equal to K, and then we can write the concentration of nitric oxide squared, since it's a quadratic relation. Now let's look at what happens when the concentration of hydrogen changes. So to figure that out, we need to first look at where the concentration of nitric oxide remains constant. This is important because you want to make sure that the rate is changing due to the change of concentration in hydrogen. Right? If both the concentrations of hydrogen and nitric oxide are changing, you don't know what it's due to. So when nitric oxide is constant, hydrogen is changing from 1 to 2, so it's doubling. What happens to the rate when that doubles? It's going from 16 to 32. It's also doubling. If one doubles and the other doubles, this is a linear relationship. So we're just going to write that as H2 to the power of 1. You don't have to write 1 though if you don't want to. And I'll get rid of this y and x for my students there. All right. So there is our rate equation. Finally, we have to determine the value of K with proper units. Please, if my students do not use proper units, I will take off a mark. So all we have to do is look at this equation, and we're going to divide it both sides by our concentrations, and we'll get K equal to the rate divided by NO squared and H2. So then we're going to plug in values. Which values are you going to plug in? Doesn't matter. Pick a trial. 1, 2, 3, 4. Anyone in the comments want to pick a trial? 3, 2, 1. No? Okay, it's just me talking. I'll do trial 1 then. Nice and simple. So the rate in trial 1 then is 0.004 units moles per liter per second. So the rate is going to be 0.004 moles per liter second. Sorry, you're too slow. I've already started. And then we have the concentration of nitric acid. That's over here. So 0.01. So we got 0.01 squared. Don't forget the squared. Actually, let's put in our units too. Don't forget the units. The units are moles per liter. And then for hydrogen, we have 0.04. Again, moles per liter. Then, this is the point where I need my calculator. So 0.004 divided by 0.01 squared times 0.04. 1,000. That's a nice number. All right, so what are our units? So let's look at our units. I'm just going to do this with a couple more steps. Let's do this on this down below. We'll do it down below. So we have moles in the numerator per liter second. And then we're dividing by, in the denominator, we have moles per liter squared multiplied by another moles per liter. So we have moles cubed per liters cubed. I can change that to just moles per liter second and then multiply. Instead of dividing, we'll multiply by the reciprocal of that fraction in the denominator. So liters cubed per moles cubed. So 1 liters, let me cancel with red. I like using red. 1 liters cancels with 1 here, so we're left with a square. 1 mole cancel with 1 mole here, we're left with a squared. So our units then are liters squared per mole squared seconds. Okay, and if it helps, your units for K will always be liters to the power of a number that is 1 less than the order of the reaction. So your order is 2 and 1. So this is, it didn't ask you for the order, but the order for this reaction is going to be 3. So 1 less than 3 is 2. So you have liters squared per, same with the moles, right? Moles to the power of 1 less than the order, so 2 seconds. Okay. So there's my review. I hope my students find this helpful and anyone else finds it helpful. Any last questions before I end the live? Anyone want to say hello to my dog? Come here. There she is. All right. Any last questions? Oh, yes. I love using red, especially on students' tests. All right, then. If there's no questions, good luck with your studying. I'll see my students tomorrow, and everyone else, have a good night.